So the title of my talk is Light from the Edge of Time. And what I'll try and do is just give you an overview of one particular topic in astrophysics that we're interested in at the moment and how we're trying to address that with our technology here in UCD. And I'd like to thank all the members of the Space Science Group for their friendship and their collaboration. Okay, so what I want to try and do is give you the universe in a nutshell. I've just been told I have 4 minutes more than I thought I had, so I can talk about this for a few minutes. And this is a visualization of the origin and the evolution of our universe as we understand it today, obviously in a very stylized version. So as you probably know, it's very popular, the idea of the Big Bang theory. We believe that the universe started in a hot Big Bang about 13.7 billion years ago. And the nature of that explosion and what was there before is obviously still shrouded in mystery. What we do know is that essentially we started with a very hot soup of particles and radiation interacting with each other. So there was quite a lot of opaque fog, if you want to think of it, at that early time in the universe's life. But as the universe expanded, creating space and time in the process, it cooled down. And gradually it cooled down sufficiently that some of those particles could form atoms. And this was the formation of neutral hydrogen atoms in the universe after about 400,000 years or so. But we can actually see the last surface just before that neutrality hit. And that last surface is called, that we now see, is called the cosmic microwave background. And what that is it's just a map of temperature in the early universe at about 400,000 years. It's called the surface of last scattering. We can't see behind the fog earlier than that in time. But we can see these minute variations in temperature imprinted on that map, if you like, of temperature variability. And what that tells us now, it's at only 3 degrees above absolute zero. It's incredibly cold. At that time, it was quite hot. It would have been very hot. But as the universe continued to expand, this temperature map is imprinted on the cosmos, and we can observe that, and we have done so with the most exquisite precision by the European Space Agency Planck telescope. Nothing will do any better than Planck. The maps we have from Planck now are the best we'll ever get. And that's important because essentially those hot spots provide the seeds for the first generations of stars that would have formed in the universe. But not before a long period here called the Dark Ages. And the reason this is dark is that background imprint was basically just a glow. Would have been a kind of permeated blue glow throughout the cosmos if any of us had been around to look at it. But there were no stars there. There was nothing. There were no point sources of light to start illuminating the cosmos. So nothing happened in terms of star formation for a long time, maybe until 400 million years or so after the Big Bang, when we believe the very first populations of stars began to form, seeded by these hot spots and slight density enhancements imprinted on the early universe. And after that, then the first galaxies may have formed at about 1,000 million years, I should say, after the Big Bang. And initially, these would have been quite small dwarf galaxies, evolving now into these beautiful spiral-type galaxies and ellipticals that we, for example, see all around us. And then to present day, after the formation of the solar system at about 8.5 billion years post-Big Bang. So that's the universe in a nutshell. But this is a big issue in cosmology. What was going on here? Because this is the theory, but we have very little in the way of observations to back up this notion that there was a very first population of stars that were probably very massive, maybe several hundreds or even more massive than our sun. And because of that huge mass, they would have evolved very quickly, ionizing the interstellar medium around them, blowing out ionized gas around them, and allowing light to pass through. But that's a heck of a long way away, and have we any hope observationally of seeing that population of first stars? If you look at some galaxies from very early universe, so 9 billion years ago, so at around here-ish, what Hubble Space Telescope is seeing, if you see all these basically invisible numbered dots here in that map, in this zoomed in image, are all galaxies. Right? This is what the early galaxies in the universe look like. They're these tiny blue dots, and they're blue because of the active star formation. Those massive stars give the galaxies a very blue color, but they're incredibly faint. So they're very numerous at that early stage in the universe, but they're incredibly faint and hard to see. So if that's what a galaxy in the early universe looks like, what hope do we have of seeing a single star and identifying the very first population of stars in the universe? So luckily we have a lighthouse in the early universe called a gamma ray burst. And a gamma ray burst is a massive explosion of gamma rays. This is an example here of one that we see with the gamma ray detector in space, going up and down, reaching a peak. And at the peak, the gamma ray burst outshines all the other sources of gamma rays in the universe combined. They're called the biggest explosions since the Big Bang itself. And we now know that these gamma ray bursts are associated with the collapse, not of regular big stars that are maybe 10 times more massive than our sun, but of really massive stars, maybe 100 times more massive than our sun, which could be, in some cases, the very early ones I mentioned a few minutes ago. This is a Vela satellite, which was the satellite that discovered these GRBs, as they're known, back in the late 60s. The Vela satellites were looking on Earth, to Earth, for violations of the nuclear test ban treaty by the Russians. And instead, they detected these unexplained flashes of gamma rays coming from the opposite direction, coming from space. And we've had many, many satellites since then. This is Integral, a European mission that we work on in the group. And here's 2 NASA missions that we also work on in the group, Fermi and Swift. So a lot of studies of gamma ray bursts have been going on. But can we use the gamma ray bursts in any way to look back in time? This is a little animation just showing you what we think is going on in a gamma ray burst. What we've got is a star which collapses to form a black hole, and this drives an outflow of material, drives an outflow of material in 2 jets. And although the initial explosion is in gamma rays, there is some visible light also produced in that explosion. And then as this jet propagates through the medium around the star, it heats it and it lights up in visible light as well. So we can actually pick up these gamma ray bursts, not just in gamma rays, but also in visible light. And now the movie doesn't want to stop. Okay, so if we think about that diagram again and think about, well, how far away are the gamma ray bursts? Most of them are quite near us, actually. So here's the age of the universe from 13.7 billion years, i.e. now, kind of back in time to 0. So many of them we see at a few billion light years away. But then we've seen a couple, just a couple. So even though they're incredibly luminous explosions that we can see to great distances, there aren't that many of them. And actually, the universe was rather small at those distances, at those early times in its life. So that's not too surprising. Here's a quasar. Quasars have been used as cosmological probes to look at the interstellar medium and star formation. The most distant is 6.43. In this diagram, it's probably a little bit out of date now. Most distant galaxies at a redshift of 7, so about 800 million years after the Big Bang. But now we have a GRB which is even further, 8.2 redshift, so 0.6 billion years after the Big Bang. So really, there's a realistic chance with gamma ray bursts to really go back and see the very, very first population of stars in the universe. And from that, we can understand much, much better how that epoch of reionization, when we went from dark ages to full-blown star formation and galaxy formation, we really don't understand that at all from an observational point of view. So it looks promising to use gamma ray bursts as lighthouses to the early universe. And if you've been to the planetarium outside, you might have seen the movie about the next generation of enormous telescopes, 30 meters in diameter and so on. And you might say, well, what could a small telescope do? How could a small telescope compete and study the early universe? How could we compete with those giants? Well, very effectively, as it turns out. And our group has built a small robotic telescope called Watcher in South Africa. So this is the High Veld in the Orange Free State near Bloemfontein in South Africa. The rugby fans among you will know Bloemfontein from many rugby matches. And it's got a very impressive observatory and lots of buildings which were no longer in use. So we asked if we could put our robotic telescope there, and we've started collaborating about 10 years ago on this project. It's a totally robotic system, so the primary mirror is about 40 centimeters, however big that is. It's got a very nice camera, cool camera on board, and a very fast slewing mount. So what happens is a satellite, such as one of the gamma ray satellites I mentioned earlier, detects one of these new gamma ray flashes in the sky, downloads the coordinates to ground, sends them out by the internet within a number of seconds, and within a minute, or in some cases within 20 seconds, our telescope slews automatically to that position on the sky and starts taking images. And so because we're so very fast, we can see that visible light from those distance explosions when they're still very bright. And so to finish, and here's some nice pictures, and it's a collaboration with colleagues in South Africa, of course, in Spain and the Czech Republic. So to finish, I'm just going to show you some images we took of an explosion. One of these gamma ray bursts back in summer 2012, and I want you to spot the gamma ray burst afterglow here. So I'll give you a clue. It's in the left-hand side of the frame. So you've got all these stars and things. This is what an astronomical image looks like. And the time stamp here is more or less regular units. So it starts at 2:46:41. Next one, 2:48:45. Okay, so keep an eye on the left-hand side. See if you can see anything changing. Try and match some patterns. Another minute or so later. Another minute or so. Anyone got any hint of a source changing? Yeah? The middle of these two? Where is it gone? That guy? Oh, good eyes. Yeah. So there it is, nice and bright. There's a slight shift between that image and the next one, but the pattern is the same. And then over a few minutes, that source just disappeared, and then it's gone. And that was a source that was about 7.5 billion light years away. And we were able to see it with our little robotic telescope. So that's how we hope to see light at the edge of time. Thank you very much.